In this video, I'll show you how to bake keyframed object animations into object animation textures. It will be a short one since most of the process is nearly identical to the previous video where I demonstrated how to bake a physics simulation into object animation textures. The main difference here is that I've animated a few objects using NLA strips. These strips were added to an NLA track, allowing the baker to automatically determine the frame range. Using an NLA track isn't strictly necessary though. You could just animate objects, say in the dope sheet, and manually specify the frame range instead. And that's really it. The rest of the process is the same as before, but I'll walk through it again quickly, this time trying out a few different options. It will be quite similar though, as you'll see. First, let's bake the position data into a texture. We'll store position in the RGB channels, mapping the X, Y, and Z components respectively. For the rotation data, I'll create a second texture, but this time, instead of baking the rotation as axis and angle, I'll bake it as a quaternion. That means storing the remapped X, Y, Z, and W components in the RGBA channels for storing in an 8-bit RGBA texture. The rest of the process is unchanged. Set the texture export path, note that the Blender file must be saved for this option to appear. Give your bake a name, set the mesh export path, and that's it. Just hit bake. Once the static mesh is imported, make sure to disable distance fields and light map generation, or at least ensure it doesn't interfere with the UV map generated during the bake. Also, make sure to disable nanite as it tends to distort UVs and doesn't work well with vertex offset animations. Just to be safe, enable 32-bit UVs, although this usually isn't required for object animation textures due to their relatively low resolution. Next, configure the bounds using the values reported by the bake tool or found in the generated XML file. Import the two textures, set the quaternion texture to RGBA8 and the position texture to 16-bit HDR uncompressed. Since quaternions can't be interpolated using standard pixel interpolation, make sure to set the filter to nearest. The material setup is almost identical to the one shown in the previous video. The only real difference is that because the rotation is now stored as a quaternion instead of an axis and angle, the material function needs to be updated to decode the quaternion. Internally, the quaternion is still converted to an axis and angle, which is then applied using a rotate about axis node. Keep in mind that since the quaternion texture is not interpolated, the resulting rotation may not look smooth. The advantage of storing a quaternion, however, is that it allows for spherical interpolation, or slurp, which brings me to this. The material functions I'm showing here are just templates, they are not strictly required. As long as you understand how the data is baked into the various animation textures and how to sample it properly, you're free to create your own approach. I've done my best to improve the user experience by providing several template functions that should cover most use cases. However, since the tool can be configured in many different ways, you might run into edge cases that aren't supported by the templates. For example, spherical interpolation. The content examples are meant to give you the extra context needed to start building your own custom material functions. For instance, in this example, the offset texture uses pixel interpolation to achieve frame blending. The rotation texture, which stores quaternions, uses nearest filtering to avoid pixel interpolation. Therefore, frame blending is done manually by sampling the rotation texture twice, once for the current frame and once for the next, and then slurping between the two based on the frame remainder. The resulting quaternion is then converted into an axis and angle, which are used in a rotate about axis node to produce a smooth animation.